Wait a second. You will see the point. No, yeah.
Okay. Welcome, everybody. It is a pleasure for me to present this session. Me and my colleague, Lucas Perez, will be the chairs of this GEFES Awards session. First of all, I would like to introduce myself. My name is Elena Pinilla. I'm a postdoc researcher at the Nanophotonics Technology Center in Valencia, in Spain, and I belong to the steering board of GEFES. I'm also vice president of the Spanish Royal Physics Society. Lucas is assistant professor at Universidad Complutense de Madrid and also associate researcher at INDEA Nanoscience. We would like to thank the amazing work done by the organizing committee of this online Congress. It is an honor to be here online with all of you today. This session is divided into 3 talks, given by the researchers who have been awarded the prizes for the best thesis in the experimental and theory categories, and best article for their outstanding work in condensed matter physics, Edurne Sagasta, Regwen Yu, and Mauro Brotons. We will present each of them previously their 25 minutes talk. At the end of each talk, we will have 5 minutes for questions that you have to send through the chat. We will read them in order of appearance to the speakers, okay? So I give the floor to my colleague Lucas to present the first talk.
Okay, thanks, Elena. So, yes. Let's see if I can do this. Yeah. So it's a pleasure for me to introduce Edurne Sagasta. She's the winner of the Best Doctoral Thesis Award in Condensed Matter Physics in the category Experimental for her studied work entitled Spin-to-Charge Current Conversion in Systems with Spin-Orbit Coupling. This work was held at TIC Nanogune in San Sebastián in Spain and supervised by Professor Felix Casanova and Professor Luis Hueso. So, Edurne has told us that she really likes the mountain and enjoying nature, and she has sent to us some nice pictures from a short stay she did in Japan. But probably these 2 pictures say us more about this character of Edurne. She's a very nice person, and it's really a pleasure for me to introduce her in this award session of the GEFES. So Edurne, this is your diploma. And this is not your diploma, your program should be somewhere here. I will show you later, but they will send to you the diploma. And now this is the audience, and congratulations on behalf of the GEFES community and also the 2 sponsors, the ICMA and the ISEMOL, for this prize. And then Edurne will present her talk, Spin-to-Charge Current Conversion in Systems with a Spin-Orbit Coupling. So it's your turn, Edurne. You can share your screen. And you can start now. So, yeah.
Okay, good afternoon to everyone. First of all, thank you very much for the nice introduction, Elena and Lucas. And thank you very much for the award. I'm very grateful for this, and also for the chance that you are giving me today to show you the work I have been doing at CIC Nanogune. Well, so today I will talk about the spin Hall effect, which is a phenomenon that occurs well, in different materials that contain spin orbit coupling and results in spin-to-charge current conversions. So let's start from the beginning, and let's see. Sorry, I cannot. Okay. And let's see then what's the spin orbit coupling and why is it so interesting and useful for. So here we can see that, of course, it's useful for scoring goals, but let's go into our matter. So what it is interesting here is that when the player hits the ball, the ball starts to spin around itself, and thanks to that, its trajectory gets deflected. So this is the phenomenon that electrons do in a material. So what we can see in a material is that if we apply a charge current in a material that contains a spin-orbit coupling, what we see is that the spin-up and spin-down electrons' trajectory is deflected in the opposite direction. So this is due to the spin-orbit coupling, and this gives rise to new phenomena and effects. And all these effects are studied in the field of spin-orbitronics. So for instance, we have spin transistors where the spin current that is flowing in the spin transistor is controlled by the applied external gate. And this is because we are able to tune the spin-orbit coupling. Now the skyrmions also are systems where the origin of the skyrmions is the spin-orbit coupling, and are systems that are widely studied in the spin-orbitronics community. And also the spin-to-charge current conversion arise due to the spin-orbit coupling. And today we will see particularly the case of the spin Hall effect. So today's talk is divided in 3 different parts. First, I will show you the results that we obtained in the spin Hall effect in platinum. Then I will focus on the spin Hall effect of tantalum, which is another interesting heavy metal. And finally, I will show you how we were able to enhance the spin-to-charge current conversion that takes place in a platinum graphene heterostructure that is interesting, the idea for technological applications. So if we go to the beginning of the story, we all know that if in a conducting material, we apply an external out-of-plane magnetic field and we measure the transverse voltage, which we see this linear relation. And this is the ordinary Hall effect. When Hall tried to measure this effect in a ferromagnetic material, he observed that there was a shift in the curves. And this is the effect that we know today that is known as the anomalous Hall effect and is originated due to the spin-orbit coupling. So what is occurring in this ferromagnetic material is that, well, first we are having the different amount of spin-up and spin-down electrons, and due to the spin-orbit coupling are deflected in opposite direction, which gives rise to a transverse voltage. So this is what we are seeing the shift in. This is why we are seeing the shift in the graphs. And notice that to see this effect, we don't need any externally applied field. Just the spin-orbit coupling is acting as an effective magnetic field. So later it was concluded that if this phenomena was occurring in a ferromagnetic material, it should be also present in a non-magnetic material. And this is the spin Hall effect that we know today. So in the direct effect, in the spin Hall effect, if we apply a charge current in a material with a spin-orbit coupling, in the transverse direction, we will have a pure spin current generation. So this is a spin current generation method. In the reciprocal effect, in the inverse spin Hall effect, if we apply a pure spin current in a material with a spin-orbit coupling, in the transverse direction, we will have a charge current generated. So the inverse spin Hall effect is a spin current detection method. The figure of merit here is the spin Hall angle because it will tell us how much spin current will be generated for an injected charge current and vice versa. Interestingly, the spin Hall effect and the inverse spin Hall effect have arisen in different experiments that we can see in spintronics. So for instance, thanks to the inverse spin Hall effect, we were able to measure the spin Seebeck effect and the spin pumping. And also both the spin Hall effect and the inverse spin Hall effect are behind the spin Hall magnetoresistance. Regarding the applications, we can use the spin Hall effect for writing the magnetic memory elements. So here we can see what is occurring is that we are having a spin orbit metal where the spin Hall effect is occurring. So if we inject a charge current in the transverse direction, a pure spin current is generated that will be able to flip the magnetic memory element. And this will occur because it's generating a spin orbit torque. In case of reading the magnetic memories, we have the case of the inverse spin Hall effect, because here we have the proposal of Intel, where they are basically injecting a current from the ferromagnetic element, which will be our memory. So here, as it is a ferromagnet, we will have a spin current flowing in the block. And due to the inverse spin Hall effect, a charge current is generated in the transverse direction that we can measure it and therefore extract information of the memory element. This, in fact, we have been, our group in CIC Nano-UNE, we have been collaborating with Intel, and we have quite recently published this paper. So I suggest to you that if you are interested on the topic, that you can have a read. So basically what we see in these two experiments or proposals is that the spin orbit metal, where the spin to charge current conversion is occurring, is useful for writing and reading the memory element. But of course, for this, we need large spin to charge conversion efficiencies. And of course, for this, we need to understand properly which mechanisms are dominating this spin Hall and the inverse spin Hall effect. So, well, I said that the charge current and the spin current in the spin Hall effect are related by the spin Hall angle. And the spin Hall angle can be written in terms of the spin Hall conductivity or the spin Hall resistivity, which are transverse conductivity and the resistivity. And here we are having the longitudinal conductivity and the resistivity of the spin Hall metal. Interestingly, some years ago, Tiana co-workers proposed a phenomenological equation for the anomalous Hall effect that were considering different contributions of the anomalous Hall effect that were explaining their anomalous Hall resistivity that they were measuring experimentally. So here we can see that the first contribution is, well, corresponds to the intrinsic contribution. And the intrinsic contribution relies on the spin orbit coupling is inherent to the electronic bands of the spin orbit metal. And then we are having two extrinsic mechanisms, the skew scattering and the psi jam, where the spin orbit coupling is coming from the impurities that we are having in the host material. We were using this phenomenological equation in our group for the first time to explain our spin Hall effect results in platinum. So here an important note is that if we are able to determine which mechanism is dominating the spin Hall effect, we will be able, this will tell us how we can enhance the spin Hall angle. So now we will jump to the results and the experiments that we did to study the spin Hall effect in platinum. So platinum is the prototypical metal where the spin Hall effect has been studied. If we go to the literature, we can see that we are having many results and the spin Hall angle value varies significantly from group to group and technique to technique. Also experimentally, not clear which mechanism is dominating the spin Hall effect. And of course, this hidens how we can optimize the spin Hall angle, which is in the end the one way of enhancing the output voltage that can be useful for applications. So in order to answer these questions, we were using the spin absorption technique to study the spin Hall effect. So the spin absorption technique is measured by using these lateral spin bulbs that consist of two ferromagnetic electrodes that are used to inject and detect the pure spin current that will be transported in the non-magnetic metal, which is in our case made of copper. So basically we are injecting a current in a closed circuit from the ferromagnet into the non-magnetic metal. And at the right side, we will have a pure spin current generated and injected into the copper that will arrive to the second ferromagnetic electrode, that is our detector, and we will be able to measure a voltage drop. That dividing by the current, we are able to get the non-local resistance. So now if we sweep the magnetic field, we are able to attain the parallel and anti-parallel configurations or parallel and anti-parallel resistance value of the two ferromagnetic electrodes. And from the difference, we get the spin signal. Now, if we fabricate another lateral spin bulbs in the same conditions, but adding a spin orbit metal in the middle, and we perform exactly the same measurement, what we see is that the spin signal that we obtain is much smaller. So basically what we are seeing here is that the spin orbit metal is absorbing part of the pure spin current that is flowing in the non-magnetic metal. This is why we call it spin absorption. So from the ratio of the two signals, we are able to quantify how much spin current has been absorbed in the spin orbit metal. Once this absorption has been quantified, we can jump to the second measurement, where we will measure the inverse spin Hall effect. So now we apply the magnetic field along the copper axis or copper channel direction, so that the spin current that is injected also points in that direction. So the spin current will be absorbed by the spin orbit metal, platinum now in our case, and due to the inverse spin Hall effect, it will be converted into a charge current, and therefore will give rise to a voltage drop that we will be able to measure, and by dividing by the current, we are able to extract an inverse spin Hall resistance. Now if we sweep the magnetic field, what we will be able is to inject the opposite, the spin of the opposite polarity, and therefore the generated charge current will point in the opposite direction, giving rise to the opposite resistance. From the difference in the resistance value, we extract the spin to charge conversion signal, and by using this equation, where we have to consider the amount of spins that have been absorbed in the spin orbit metal, we are able to extract the spin Hall angle value. Of course, as I showed you before, if we know the spin Hall angle value, we also know the spin Hall resistivity value and the spin Hall conductivity value, considering the equations. So now we perform this experiment at different temperatures. So here we can see the result. So in the end, what we are able is to plot the spin Hall resistivity value, because we extract from the spin Hall angle, and as a function of the square of the platinum resistivity, because we know which resistivity of platinum corresponds to each temperature. So I'm plotting as a function of the square of the resistivity, because in this way, considering the phenomenological equation, we know that the slope will give us the intrinsic spin Hall conductivity, and the intercept will give us information of the extrinsic contribution. In fact, in platinum, it was demonstrated, or it can be argued, that the Psi-Yang contribution is negligible. So this is the experiment that we did for a single device, but we decided to make more samples. So here we can see the result obtained for multiple devices. So we fabricated some lateral spin bulbs where the platinum wire, nanowire, was spattered, and other lateral spin bulbs where the platinum was evaporated. They are characterized by lower resistivity, as you can see, the ones where the platinum was evaporated. But interestingly, what we are obtaining, considering all the devices, is a constant intrinsic spin Hall conductivity. We see that the slope inside the error bar is the same for all of them. And we extract a value 1,600 on -1 centimeter -1, which is in good agreement with the theoretical report that we can find in the literature. Regarding the skew scattering angle, we see that it changes from 1 to 2% and is slightly different for the spattered and for the evaporated data. Now we will show you, here we can see the spin Hall angle value that we obtain as a function of the platinum conductivity. So now if I plot here only the intrinsic contribution, this is the black solid line, we see that the spattered data nearly merge into this black solid line. However, to explain the high conductivity data, we need to also consider the skew scattering contribution. Note that we are in the logarithmic scale. So what we are seeing here for the first time is the crossover between the moderately dirty and the super clean scaling regimes in the spin Hall effect. And we are reproducing the large dispersion in literature, because just by modifying the resistivity, we have been able to tune the spin Hall angle from 2% up to 14%. Also, we have unveiled which mechanisms are dominating the spin Hall effect. We see at the high resistive regime, the intrinsic mechanism dominates, and at high conducting regime, the extrinsic one. And also, we are showing a path to that shows how to optimize the spin Hall angle, which is to increase the resistivity of the material. So now I will jump to the second part of the talk, where we will see the spin Hall effect in tantalum. So again, if we go to the literature, we can see that there are many different results. First of all, we need to clarify that in case of tantalum, we can find generally two phases. We have alpha phase that is metallic, and beta tantalum, which is it's characterized by a higher resistivity and with a negative temperature coefficient. So in general, what we can see that is that in some of the cases, in some of the works, just with the resistivity, they determine which is their phase. We can also see that the spin Hall angle value, so we can see some dispersion in the spin Hall angle value from group to group and technique to technique. And experimentally, there is no quantification of which mechanism is governing the spin Hall effect in tantalum. So in order to investigate more on this, we have performed again the spin absorption experiment by using lateral spin valves where now the nanowire, the spin orbit metal will be made of tantalum. And here we can see the resistivity of the tantalum. We see that here the corresponding coefficient is, well, this curve shows that the resistivity is characterized by a negative temperature coefficient, and the variation of the resistivity with the temperature is very narrow. This corresponds with beta tantalum, but we decided to make the phase characterization experiment by doing transmission electron microscopy experiment. And what we saw is that we are having the coexistence of alpha and beta tantalum phases. Importantly, the beta phase is the one that is on the top. And this is important for us because in the lateral spin valve, we will have the spins arriving from the copper channel that will be injected at the top side of the tantalum nanowire. So the spin to charge current conversion will occur in the top side, so in beta tantalum. And importantly here, what we can say is that just measuring the resistivity is not enough to determine the phase. So now we will jump to see the results that we obtain in the lateral spin valve. I basically perform in the same way as I just explained for platinum, the experiments of the inverse spin Hall effect. And here we can see the results as a function of temperature. So in the end, in the same way, we can plot the spin Hall resistivity as a function of the square of tantalum resistivity, so that the slope is giving us again the intrinsic spin Hall conductivity, which is negative for tantalum, and this is in agreement with what is expected theoretically. And we obtain minus 910 or minus 1 centimeter minus 1 value. And regarding the extrinsic mechanism, we see that is positive. Again, now as the resistivity regime that we are studying is very narrow, we decided to make multiple devices and make the experiment at different, just at low temperatures, because the variation of the resistivity with the temperature is very narrow. So then we can write the phenomenological equation for low temperatures, which basically is to write the resistivity substituted by the residual resistivity. So we can write it in this way. So here we see the results that we obtain for the 7 devices, 7 lateral spin valves that we fabricate made of tantalum, where we can see now that the resistivity varies much more. So from the fitting, we can extract now the slope will give us the intrinsic plus the side contribution. And if we compare the value with the value that we obtain for the single device, we see that they are compatible. So this led us to say that the side contribution is negligible in the case of tantalum. And if we compare with the theoretical results, we can see that the theoretical results show a much smaller value. In case the skew scattering angle, we see that is positive and quite large value. So now we can compare the platinum and the tantalum devices, and what we can see here is that the slope that corresponds to tantalum to platinum is much larger because the intrinsic spin Hall conductivity is much larger. However, we are able to obtain very large spin Hall angle value, minus 35%, which is the largest published for a pure metal. So now the question that we may ask is, okay, how can we go beyond? How can we enhance our output voltage in order to be useful for technological applications? So this question we will answer in the very last part, and I will start from the very same plot because we can extract very interesting information, much more information from here. So now we will take just one platinum device and one tantalum device where they are characterized with the same spin Hall angle. So we see clearly that the resistivity, the corresponding resistivity is much larger for the tantalum. So this means that if the spin Hall angle is the same, the charge current that will be generated will be the same, but the voltage drop that we are expecting for tantalum, which will be almost 1 order of magnitude larger because of the higher resistivity. If we see the results, we see that this is not, of course, it's larger for tantalum, but not almost 1 order of magnitude. So what is occurring here? The point is that we are having shunting effect. So what is the shunting effect? Due to the difference between the copper resistivity and the spin orbit metal resistivity, because the resistivity of copper is 2 micron centimeters more or less, part of the charge current that is generated in the spin orbit metal flows back into the copper, giving rise to a smaller voltage drop. So a larger resistivity, we said, gives us larger spin Hall angle, but on the other side, gives more shunting effect. So we are limited here. So our approach was, instead of modifying the spin orbit metal, why don't we substitute the copper by a more resistive material so that we can overcome the shunting effect? So this is why we decided to use graphene, because it's characterized by a long spin diffusion length, as long as copper. In fact, in case of graphene, is constant with temperature, and in case of copper, it decreases with temperature. So this factor we have in favor. And also the shear resistance is much larger than in case of copper. So we make the same inverse spin Hall experiment, and here we have the results as a function of temperature. So now I plot just the spin to charge conversion signal as a function of temperature, and we see that it increases with temperature. So now if we compare to the metallic lateral spin valve results, we see that they are here below. We need to zoom them to see a bit better. So we are seeing a great enhancement in the spin to charge conversion signal. So let's clarify where is coming this enhancement, which is the origin of this enhancement. So first of all, we said that we are overcoming the shunting effect. In platinum graphene, we overcome this shunting effect. So this is one of the reasons we are seeing a big enhancement, but also we are seeing a change in the tendency of the curves with the temperature. And this is due to the spin diffusion length that is telling us how far the electron can transport the spin without losing it. So we see that in case of copper, it decays with the temperature. This is well reported. We know that it decreases with the temperature. So this is the origin of the decaying of the signal. In case of graphene, the spin diffusion length is constant. So we should expect a constant signal. However, we know that the spin to charge conversion signal is proportional to the spin Hall angle and to the resistivity. And both are increased when the temperature is increased. Therefore, we see this increase in the signal of the spin to charge conversion. So in the end, due to all these factors, what we have been able is to enhance almost 2 orders of magnitude, almost 70 times or almost 2 orders of magnitude, the spin to charge conversion signal that is useful for applications at room temperature. So with this, I would like to summarize the talk. So first of all, we analyzed the spin Hall effect in platinum. We saw for the first time the crossover from the moderately dirty regime, where the intrinsic mechanism is dominating the spin Hall effect in platinum, to the super clean metal regime, where the skew scattering starts to take relevant part in the spin Hall effect of platinum. We have been able to extract the intrinsic spin Hall conductivity value experimentally, and also we are showing a path to enhance the spin Hall angle, which is to increase the resistivity of the material. In case of tantalum, we have been able to extract again experimentally the intrinsic spin Hall conductivity value, and to report the largest spin Hall angle value for a pure metal, which is minus 35%. And in the last part, I have shown you a novel device where we have combined graphene and platinum, because this system here we are able to overcome the shunting effect and obtain very large spin to charge current conversions at room temperature. So with this, I would like to thank all the collaborators of all this work, in particular also the Nano Devices group of CIC Nanogune, also the funding, and all of you for your kind attention. Thank you very much.
So thank you very much, Edurne, for this very nice and interesting talk. So now we have time for a few questions. Just to write it in the chat, and Elena or I will ask the questions. So, Jose Mari, could you please write the question? Okay.
Okay, maybe
No,
we can
maybe
allow
can,
him to, yeah, because
yeah,
we
yes, yes. I'm trying to do it.
huge amount, so yeah.
Okay, can you hear me?
Yes.
Yes.
Yes, so first, congratulations for the talk. Very nice work. So, yeah, so the effect you observe is very similar to what was observed in the past with the anomalous Hall effect, that the effect was larger when the resistivity of the material was larger. But of course, you pay some cost, because then the electrical noise is larger, because the thermal noise is larger, because the resistivity is larger. So my question is, if you observe the same effect with the spin Hall effect, that when the resistivity is higher, you have larger effect, but you have higher noise? Because I have seen in your graphs that the error bar is larger when the spin Hall angle is larger, so when the resistivity is larger. So I guess that you have the same effect, that you have higher electrical noise.
Yes, so thank you for the question. Here there are several aspects. First of all, this error bar is coming also because, let me show you the equation. Let's clarify where is the error bar coming from. Sorry, I have to go up. Here it is. So here we are having different inputs to the equation, to extract the value. So we are having, well, no, sorry. Here, you mean the direct, just the spin to charge conversion signal, not
Yes.
the spin Hall angle error bar. You mean just the direct, the
Yeah,
measure.
so the noise you have in the measurements, because the thermal noise, which is proportional to the
Yes.
temperature and the resistance, will be higher.
Yes, in general, yes. At higher temperature, the noise that we are having is larger. Yeah. And that it's more significant in the lateral spin valve when we are measuring the other experiment, the spin absorption measurement, because the signal is smaller sometimes. Yeah.
Okay, thank you.
More questions?
Yeah, I have one myself, if I can activate.
Okay, Elena, yes?
Yeah, sorry that I don't see how to reactivate my video. It's okay, you don't need to see me. I just was wondering, in the spin Hall effect in platinum, in the plot, you put the dependence of the temperature. Can you, I think it's...
Here?
Yeah, it looks really noisy to me. How do you manage to, well, okay, it's noisy when you plot all of them together, right? It was so fast that I couldn't see the, yeah, I was wondering how did you manage to get the data from there, but I see, yeah, because it looks like they overlap a little bit, right?
Yeah, the point is here that when we are sweeping the magnetic field, we can stop the magnetic field at certain points and make many measurements so that we get a nice average there.
Ah, okay, okay.
Yes. But then, of course, you can also see in this graph that the effect of the temperature, I mean, if you increase the temperature, the noise is bigger and bigger, is what Maria was commenting before.
Yeah, yeah.
But yeah, it's the amount of points. Also, the other thing is if you inject the current, the voltage drop also increases, and the noise doesn't. So in principle, because we are somehow it's a non-local measurement. The current goes towards one side, the charge current that we are injecting. So by injecting larger currents, also it improves the measurement. However, you have to be careful because you are having nanowires and you can break them.
Yeah, yeah, I see. Thank you so much.
Okay, so probably it's time to switch to the next talk. Thank you very much, Edurne, for the talk, and congratulations for the work.
Thank you very much.
Okay, so sorry, I think I have to go on with the presentation for the next speaker. So, okay. So we go on with the session, with the second talk that will be given by Renwen Yu. So he's the winner of the Best Doctoral Thesis Award in Condensed Matter Physics in the category of theory for his outstanding work entitled Toward Next Generation Nanophotonic Devices. So I would like to speak a little bit about Renwen. He received his bachelor degree in optoelectronics and information engineering from the Huangsong University of Science and Technology in China in 2011. He received his master degree in 2014 for the Faculty of Physics and Astronomy at the University of Jena in Germany. And finally, he received his PhD degrees in 2019 from the Universitat Politécnica de Catalunya. He is currently a postdoc researcher in theoretical nanophotonics with Professor Javier García de Abajo at IPFO. Renwen, you have your diploma here if I'm able to share my screen quickly. Okay. Here, sorry that I want to, okay. So this is your diploma. So here you can see Renwen in a very nice picture he sent to us for his presentation. And with this, we send you all the congratulations from all the GEFES community and from the sponsors of these prizes, the Instituto de Ciencia de Materiales de Aragón and the Instituto de Ciencia Molecular de Valencia. So I stopped sharing my screen. And please, no, I didn't stop it, but I'm doing it now. Okay, so please, you can go on with your talk. Welcome, Renwen.
Thank you, Anina, for the nice introduction. So good afternoon, everyone. So first, I would like to thank the GEFES committee members to give me this valuable prize. And also, I would like to thank the organizers to give me the opportunity to present my work here. So today I'm going to talk about towards the next generation nanophotonic devices. So which is quite different from the most of the talks in this conference because they are mainly talking about transport or electrical or magnetic properties of condensed matter systems. Here I will mainly talk about optical or photothermal properties of nanoscale systems. So as you know, so basically optics is a very old field. And in my opinion, there are three pillars to push optics into its modern area. So first, it's the invention of lasers. So it provides coherent light sources for a lot of applications. And the second is the successful reduction of loss in optical fibers, which makes long distance, high bandwidth communications possible. And the third is the introduction of semiconductors into optical business. And then people have developed light emitters and optical modulators and many other optical devices. And in general, there are two trends in the development of optical devices. The first one is the miniaturization. As you can see, nowadays, people can make on chip optical sensors for blood test. And the second trend is about the introduction of new materials. So starting from silicon or 3,5 compounds. So now people can make ultraviolet LEDs based on gallium nitride. And the miniaturization of optical devices witnessed the rise of nanophotonics. So there are lots of applications in the field of nanophotonics, ranging from metal materials with negative permeability to hot electron enhanced photocatalysis. And many of these applications are based on the excitation of plasmas. So plasmas are collective oscillations of conduction electrons in systems with metallic behavior. That means the real part of the permeability is negative. And the plasmas can concentrate light into subwavelength region because the plasma wavelength is way much smaller than the free space light wavelengths. And due to this strong light concentration, it can create huge field enhancement and which can be used for optical sensing. And the light shape of the optical spectrum of the plasmonic excitations are sensitive to geometry, to the material, and also to the environment in terms of the permeability of the environment. And for noble metal-based plasmonic systems, the resonances are typically invisible to near-infrared frequency range. So here, I'm providing an example of plasmonic excitations. So basically here we have two gold nanostars with different shapes. And from the far field optical spectroscopy, we can see two different peaks associated with these plasmonic excitations inside these two different nanostars. And at the resonance peak, when we look at the field distribution, we can see that we can have a 3 order of magnitude enhancement of the field at the tip of the nanostars. And the other trend, which is about the introduction of new materials, make a great deal in the last decades, especially about the introduction of these two-dimensional materials and of course graphene. And these two-dimensional, as you know, so the two-dimensional materials have a lot of applications, not only in nanophotonics, but also in nanoelectronics. And here, in my thesis and in my PhD study, I mainly concentrate on the use of graphene. So as you know, so graphene is a honeycomb, is a two-dimensional honeycomb lattice of carbon atoms. And here I'm presenting its electronic band structure close to the K point, where the conduction band is in touch with its valence band at this single point called the Dirac point. And due to its peculiar band structure, graphene can have very high carrier mobility. It can provide broadband absorption of light. And due to its two-dimensional nature, it has very low electronic heat capacity. And when graphene is doped to certain Fermi level EF, and considering only its intraband transition, its optical conductivity can be expressed in this Druder-like expression. And as you can see, so since it's basically a metal, when it's doped. So it can support plasmonic resonances, just as noble metals. So in fact, so graphene plasmas has been observed already 8 years ago, and its wavelengths, the plasma wavelengths of graphene can be expressed into this expression, where alpha is the phi structure constant, and just insert some typical values, we can see that the plasma wavelengths of graphene can be 60 to 70 times subwavelengths, so it's extremely subwavelengths. And it can provide strong near-field confinement, even stronger than the noble metal. And as you can see, so basically if one can tune the doping level by electrical gating, one can tune the plasma wavelengths as also observed in the experiments. So graphene is a really is an active tunable material for many optical devices. And different from noble metal-based plasmonic systems, graphene plasmas are in the infrared to terahertz resonances. So it's at much lower energy or much longer wavelengths range. So in my thesis, I have did a very diverse topics. So in the first part, I have made an analytical modeling of localized surface plasmas, which I provide an analytical model to calculate the optical extinction of noble metal-based plasmas with negligible computational efforts. And in the second part of my thesis, I have made investigation of graphene integrated with optical cavities in order to achieve strong light modulation. And in the third part of my thesis, I've provided a new sensing mechanism based on graphene nanostructures to achieve sensitivity down to single charge level. And in the fourth part of my thesis, I have explored a method based on photothermal manipulation of graphene to achieve nanoscale zero management. And in the final part of my thesis, I have provided a nanostructure based on graphene nanojunctions to achieve with a mid-infrared light detection. So today, due to time limitation, I would talk about only the first, the second, and the fourth parts of my PhD study. So now let's go to the first part of my talk today, which is about analytical modeling of localized surface plasmas. So basically, nanophotonics is about making nanostructures. So based on different design of nanostructures, one can achieve different functionalities such as magnetic metamaterials or to even an invisible clock. And these nanostructures are based on nanoparticles, which are the fundamental elements of nanophotonics. And of course, different types of nanoparticles, such as U-shaped nanoantennas or split ring resonators, they have different optical response. So the question is, can we find a simple analytical or semi-analytical model to describe the optical response of these plasmonic nanoparticles? So, in the first case, I would like to talk about the analytical distribution of localized graphene plasmas. So let's considering a graphene nanostructure with an arbitrary shape, and its characteristic length is d. And we know that graphene plasmas are extremely subwavelengths. So basically, we can treat them in the electrostatic limit. And considering the presence of the nanostructure, the self-consistent field can be expressed in this equation. And after defining the normalized field and the normalized spatial coordinates, we can get this eigenfunction, where this EJ is the eigenfunction, and the M is the capital M is the non-local operator, and the inverse of the eta J is the eigenvalue. So after solving this eigenfunction, we can have these so-called plasma wave functions, which is related to the induced charge distribution. And the blue and red colors indicate the charge with different size, like positive or negative charges. And the optical polarizability can be decomposed as a summation of all these optical modes supported by these different graphene nano structures of different shapes. And this mode dipole moment can be calculated from the mode eigenfunctions, and the mode eigenvalue can be obtained straightforward after solving the eigenfunction. And note that these two parameters only depend on the shape of the nanostructure. It doesn't depend on its material. It doesn't depend on the size. It doesn't depend on the environment. It's only depend on the shape. And after solving this eigenfunction, here are these two parameters for the first dipolar modes, which are obtained for these listed shapes, like discs, squares, or ribbons, all the shapes. And within only these two parameters, we can do a benchmark calculation to compare our semi-analytical model with fully numerical calculations. And as you can see, no matter what's the doping level, no matter what's the lateral size of the geometry of the nanostructure, and no matter what is the permittivity of the environment, our analytical or semi-analytical model matches very well with the numerical results. And I would like to mention that all these calculations only take less than 1 minute, all of them. So that means it's a very efficient method. And however, this is just the part of the nice story. It's just the part of the story, because we know that if you are considering noble metal-based nanostructures, it's not as subwavelength as graphene-based nanostructures. So we are not in the electrostatic limit. We are in the so-called quasi-static limit, and the retardation effect needs to be taken into account. And in order to solve this problem, we can take the electrostatic eigenfunctions as unperturbed solutions and treat retardation effects as perturbation. Then we can add some correction parameters to these two unperturbed parameters to get the correct optical response. So give you an example. So basically here it's again the optical polarizability for noble metal-based three-dimensional structures, which can be also decomposed into a summation of the eigenmodes, where now is Vj is the eigenmode value, and the epsilon j is the eigenvalue, mode eigenvalue, and this is in the electrostatic limits. So in order to solve the problem in the quasi-static limit, we need to take radiation collections into account, which appears as this AJ term here, and this AJ term depends on S, which is the size parameter, depends defining how subwavelength is our nanostructures. So basically, as you can see, so basically it can be decomposed as the S to the power of 2 to the power of 3 to the power of 4. So basically you can go so on and so forth. So basically this is a perturbation series to this problem. So after using this trick, we have made this analysis for all of this large collection of nanostructures. And just give you one example, we compare our theoretical semi-analytical calculations with experimental results. And as you can see, with very little time, we can get a very good agreement between our theoretical calculations with experimental data for different types of disks made either by gold or alumina, and with different sizes indicated by different colors. So this is just take-home messages for the first part of my talk today. So we have developed an analytical model to calculate the optical response of plasmonic nanostructures with very high efficiency, and we can take irradiation effect into account by using a perturbation theory, and which can be used to reveal the physical origin of the retardation effects. So here comes the second part of my talk, which is night modulation with graphene. So as I have mentioned, so graphene plasmas are typically in the mid-infrared to terahertz frequency range, as you can see here. So basically, by nano-patterning graphene, extended graphene to graphene nanostructures, it can support localized plasmas in this mid-infrared frequency range. And its plasma wavelength is proportional to the lateral size of the nanostructure and inversely proportional to the doping level of graphene. So in order to push this plasma resonance wavelengths into visible to near-infrared frequency range, one need either greatly decrease the lateral size of graphene nanostructures or increasing greatly the doping level of graphene. However, either way is technically challenging. So one needs to think an alternative way to do night modulation with graphene. And the alternative way is to use the interband transition provided by graphene. So here I'm showing again the band structure of graphene close to the K point, the direct point. So when graphene is undoped, so the electronic transitions of a broad band energy are allowed, which makes graphene very lossy in a broad energy range. However, when graphene is doped to certain Fermi level EF, electronic transitions with energy less than twice the doping level is forbidden, which makes graphene less lossy. And when one consider an external light is impinging onto an undoped graphene film, we can calculate its absorption by this formula, where alpha is again the phase structure constant, and we can find the well-known 2.3% light absorption in a broad wavelength range. And this broad band light absorption has also been observed experimentally. And so basically, even with this effect, it can only provide a very small amount of absorption. So in order to boost the light absorption as well as the light modulation, one can think of increase the field enhancement at the graphene plane. And in order to do so, we can integrate or invert a graphene layer in the center of a fabric polar cavity defined by two Bragg mirrors. And by a careful design, we can have a maximum field enhancement at the center of the cavity. And after boosting the field enhancement at the graphene plane, we can boost the light absorption graphene as well as the light absorption as shown here. So basically, when we change the doping level of graphene from its undoped state gradually to a highly doped state, we can have a unit order change in transmission. So basically from 100% to 0%, or close to 0% at wavelengths around 740 nanometer. So people has followed this idea, and they have built up a mathematical cavity. Instead of these two Bragg mirrors, they are using two metallic films as two metal mirrors, and they have achieved a modulation depth in reflection around like 20% in their experimental study. And so besides using this fabric cavity, one can also think about other means. For example, one can integrate graphene with low metal-based structures. And apparently, people have been thinking about this this method in basically mid-infrared wavelength range, and but due to the Bucket losses from the metallic structures in the mid-infrared wavelength range, the modulation depths are very small, as you can see here. So in order to achieve light modulation with graphene in combination with metallic structures in invisible frequency range, we are coming up with these hybrid structures, which composed of graphene and on top of ultra thin layer of silver. And when we calculate the plasma dispersions of these hybrid modes inside, supported by this hybrid structure, we can see that when graphene is highly doped, we can have a very bright and sharp plasmonic resonances in a broad photon energy range. However, when we decrease the doping level of graphene, we can see that the plasma resonance with energy larger than twice the doping level is damped. And furthermore, when graphene is undoped, the dispersion is completely blurred in this broad photon energy range. So this means with this hybrid structure, we can do light modulation. And then in order to excite those plasmonic modes supported by this hybrid structure, we can pattern the extended silver films into a periodic array of silver ribbons. And when we look at the reflection, we can see that when changed the doping level of graphene from its undoped state to doped state, we can have more than 40% light modulation in reflection at a photon energy around 0.9 eV. So the take-home messages for this part. So we have shown that monolayer graphene can be used to produce unit order changes in the optical response, and fast resonant light modulation at telecom wavelengths is achievable using moderate doping levels. So now here comes the last part of my talk, which is photothermal manipulation with graphene. So in order to do photothermal manipulation of the optical response in nanosystems, we would like to use a material, the optical properties of which are very sensitive to the temperature. And luckily, graphene is this kind of material. Actually, we can express the optical conductivity of graphene in terms of its intraband and interband transitions. And both transitions actually are temperature sensitive, as you can see here. So when we just increase the temperature, it can provide a similar effect as doping. So heating can be equal to doping in this example. And if you look at the far-field response, we can see that the heating and the doping, the heated graphene and doped graphene can provide a very similar optical response in the far field. So following this line, we think about something interesting. So basically here, we just have assumed there are two pump beams coming from the far field, and they create interference patterns onto the graphene plane. And the light intensity on the graphene plane can be given in this expression, which is, of course, depends on the spatial coordinate x. And due to this light intensity distribution on the graphene plane, we can have absorption power density of light in the graphene plane. And from this absorption power density, we can calculate the elevated exchange temperature as a function of x. And then we can have a periodical spatial distribution of optical conductivity of graphene just by optical pumping. And as you can see, by doing so, we first have a periodical distribution of electron temperature as shown as these red curves. And correspondingly, we have periodical distributions of the real and the imaginary part of graphene optical conductivity. And by doing so, when we look at the probe spectrum, here we are showing the probe spectrum, we can see by changing the pump intensity in the probe spectrum, we can have plasmonic resonances at different frequencies. And in fact, this periodical pattern of this graphene optical conductivity provides as an effective grating to couple the probe light into these plasmonic resonance modes inside this system. So basically here we achieve this all optical excitations of graphene plasmas. And by changing the pumping light intensity, we can change the excitation frequency. And furthermore, I would like to first introduce the idea of hyperbolic materials in the optical society. So basically, hyperbolic material is a kind of uniaxial anisotropic material, and basically its permittivity tensor can be given by this form. And if one of this term, either epsilon parallel or epsilon perpendicular, is negative, then we can have a very peculiar shape of these isofrequency contours. It becomes hyperbolic. And it can have lots of applications in terms of spontaneous light emission enhancement or radiation pattern control. It has lots of applications. And in order to have these materials, one can simply make a stack of dielectric and metal films, just like this, very simple. So here, I am considering these stacked materials composed by graphene and some dielectric materials. So basically, due to this two-dimensional nature of graphene, so the epsilon perpendicular, so I mean the permittivity along the z direction is a constant and is positive. However, when we look at the permittivity parallel, which is the in-play permittivity of this effective metamaterial, we can see that it can change sign when we change the frequency. So it goes from negative to positive when we increasing the light frequency. And more interestingly, when we increase the temperature, we can shift the epsilon equal to 0 frequency from lower frequency to higher frequency, basically. And by doing so, when we look at one specific frequency here, it's about 42 terahertz, when we can see that we can control the isofrequency contour at this particular frequency by simply heating graphene. And the isofrequency contour changes from elliptic shape to hyperbolic shape when we increase the temperature. And as a result of this topological valuation, we can see that when we increase the graphene temperature for example, again at the frequency of 42 terahertz, we can have an enhancement of the local density of state. It's about the 3 orders of magnitude enhancement of local density of state when we increase the temperature due to the topological valuations by heating graphene. And again, we can also see that the local density of states with large values extended to higher frequencies, as one can see before, that because of the the epsilon near 0 frequency, it's shifting to the higher frequency as we increase the temperature. So basically, we shift the hyperbolic shape also into the higher frequency. So it gives higher local density of state enhancement. So it can provide an active and potentially ultra fast control of the decay rate of the nearby optical emitters. So in order to show it's really ultra-fast topological transition, so here we are thinking about a pump probe setup. So we are using an optical pulse pump and an electron probe. So first, so we calculate spatial temporal dynamics of the electron temperatures in graphene, and as a result of this of the electron temperature dynamics, we can calculate the electron energy loss spectroscopy of the probed electron, and we can see that we can have some very high ES value in this region enclosed by the blue dashed curves. Actually, inside these blue dashed curves, we have the spatial temporal region with hyperbolic isofrequency control. So more importantly, as you can see here, within 1 picosecond time scale, the topology of the isofrequency control transforms first from elliptic to hyperbolic. Then we have very large ES value. Then it goes back to elliptic. So basically, we have really ultra-fast topological transition in this case. And another application of this ultra-fast topological transition is that we can engineering the beam steering in the far field. So as an example, here we have two optical emitters sitting in front of this cylindrical metamaterial lens, bounded by these two semi-circles. And when the temperature is at graphene, the electron temperature of graphene is at room temperature, we can have multiple lobes in the far field. However, when we change the electron temperature due to the modification of the isofrequency contour, we can modify the radiation pattern of these two emitters. And as a result, we can have this directional light emitting towards these two directions. And in the far field, we only have these two lobes.
Okay,
so,
when you are out of time, okay?
Okay,
so,
okay. So I will just go very fast.
Okay.
So
great.
let's just take home messages and just the concluding remarks of my talk and of my talk. These three parts. And thank you for your attention.
You are very welcome. Congratulations again for this very, very nice work. We are going to open the microphones, or to be able for the people to open their own the microphones to make some questions. So we have time for one very short question. If anyone wants to say anything, it's the moment. Okay, then I have one myself. I was very interested in the way you can induce this periodicity in the surface of graphene by pumping with two sources, right?
Yeah.
So I'm guessing that you can create a pattern, and if you change this pumping, then you can you tune this pattern? I mean the
Yeah.
periodicity of the pattern.
Yeah. Yeah.
With
so
any
basically,
type of light, or
yeah. So so basically there are two ways of changing the pattern, as you can see here. So basically one way is of course change the pumping light wavelength, lambda. And the other way is to change the angle of incidence. So basically by doing so, you can change the period of this pattern. And then you can change the resulted probed optical response.
And then does it mean that locally you have like hot spots
Yes.
periodically located into the surface, right?
Yes. So basically, the hot points basically is shown here.
Yeah.
So basically, as you can see, so this is the red curve is the electron temperature, and it's as a function of the spatial distance, and you can have high temperature and the low temperature, and it shows a certain periodical pattern due to the pattern of the light, interference light.
And has been experimentally measured, or?
And so this part, no. So people are, our collaborators are trying to do this.
Okay.
Yeah,
I will expect for the results.
Yeah.
That's very nice.
Let's wait.
Okay. Thank you so much.
Thank you.
I congratulate you again. So I think I give the floor to my colleague Lucas. And Lucas, we can go on with the last speaker.
Okay. Okay, so finally we have the pleasure to enjoy the third talk of this session by Mario Brotons that has been awarded the distinction of Best GEFES Paper of the year 2019, published in Nature Nanotechnology. And the paper is entitled Coulomb Blockade in an Atomic Thin Quantum Dot Coupled to a Tunable Fermi Reservoir. So Mauro studied physics at the University of Valencia, and he did a PhD at the Material Science Institute under the supervision of Juan Francisco Sánchez Royo. And then he moved to Edinburgh to start a postdoc at the Quantum Photonics Laboratory at the Heriot-Watt University, where he has continued working with 2D materials from a more quantum point of view. So he has also told us that he has always been a sport lover. Before he moved to Edinburgh, it was more about sports indoor. But although since he arrived in Scotland, he has been enjoying more outdoors things. That's quite curious because the weather there is not as good as in Spain, or at least that's in Valencia, but it's quite nice. So he said that it's impossible to stay at home with the Scottish Highlands so close. We can check that in these two pictures of two residents hiking nearby. So now Mauro will present his talk, Quantum Dots in Two-Dimensional Heterostructures, and this will be the last talk of this session. So Mauro, you can start whenever you want.
Well, thank you very much for the nice introduction, Lucas, and hello to everyone. I'd like to start by thanking the GEFES for the award and for giving me the opportunity to show this work here in front of you all. So today I'd like to show you some of the results of my postdoctoral research in the Quantum Photonics Laboratory, where basically I've been investigating quantum dots in two-dimensional heterostructures. Okay, so I decided to divide the talk in two parts. In the first one, I'd like to show you how we managed to achieve charge tuning of a quantum dot in a two-dimensional material. Okay, and this is the work that has been highlighted by GEFES. But if I have time, I'd like also to show you in a second part of the talk how this research has evolved and how it's possible to use the Moiré superlattice created in a van der Waals heterostructure to create quantum dots. Okay, so yeah, let's start with the first part. So the quantum dots that I'm going to be working with are quantum dots in tungsten selenide. Tungsten selenide is a transition metal chalcogenide semiconductor in the monolayer form, where it has broken inversion symmetry. It's a direct bandgap semiconductor, and the bandgap is located at the corners of the hexagonal brilliant zone, the so-called K plus or K minus valleys. And in these corners of the hexagonal brilliant zone, we have the band 8 states that are the generating energy in the two valleys, but they are non-equivalent, and we have spin valley lockings, which basically means that if we change valley, we change the orientation of the spin. So it was, I think, in 2015 and early 2016, it was reported, it was demonstrated by several groups, that tungsten selenide host single photon emitters. Okay, and since then it's been demonstrated that it's possible to have a spectrally isolated and spatially isolated single photon emitters in this two-dimensional material, and that these single photon emitters have a very good single photon purity. So since then, well, people have been trying to deterministically control the number of, let's say, the charge state of these quantum dots, which basically means controlling the number of electrons or holes that you load into the quantum dot. And the way that this is traditionally done in 3-5, or let's say traditional quantum dots, well, I show you later. I wanted to show you something else before. In tungsten selenide, it's possible to use strain to induce to have deterministic positioning of the quantum dots. Okay, so I wanted to show you here a few works that where basically what the people did was to take one of these layers and transfer it on top of an array of nanocolumns, and the strain generated by the nanocolumns basically, as you can see here, gives rise to an arrays of quantum dots in photoluminescence. So now we can go to what I was mentioning. So the way people traditionally control the charge state in a 3-5 quantum dot is the following. So we have our quantum dots. Basically, you have here with our confined states, and these confined states are separated by a tunnel barrier from a, let's say, reservoir of electrons, in this case, a Fermi reservoir, that's basically in the back contact. And by applying a voltage gate between the back contact and the top gate, basically we can tune the energy difference between our confined states and our Fermi level, okay? So if we think about the point of view of photoluminescence experiments, basically this means the following. So we can imagine the following, let's say, scenarios. First one is a scenario more or less like this, in which we have a neutral exciton in our quantum dot, and our Fermi level lies far below our confined energy level for the electrons. So if our tunneling time is faster than the recombination time, this basically means that we'll have no photoluminescence. But we can change the situation basically by changing the voltage gate, and we can go to a situation like this, where basically now our Fermi level lies above the energy level of the confined electron. So basically this electron cannot escape. So we have emission from a neutral exciton, which is basically formed by one electron and one hole. But now one could think that a second electron could also be loaded in the quantum dot. But the point here is that due to the presence of the first electron, in order for a second electron to tunnel inside the quantum dot, this second electron has to overcome the Coulomb repulsion with the first electron, right? And this is why this is known as Coulomb blockade, because this first electron is preventing the tunneling of a second electron. But now we can keep increasing the voltage gate and increase this energy difference, and this way overcome the Coulomb repulsion and load a second electron. And this can keep going on, so you can keep increasing the voltage and start loading one by one electrons in the dot. Okay, so we wanted to do this with our two-dimensional material, and for that we decided to exploit the properties of van der Waals materials, which basically offered us a large variety of materials with different intrinsic properties. We have insulators as hexagonal boron nitride, semi-metals, graphene, superconductors, and a wide variety of semiconductors. And on top of that, with these van der Waals heterostructures, we can combine them and stack different materials without any kind of, let's say, restriction. So we decided to fabricate a device that looked like this, where basically we had our active layer, which was a monolayer tungsten selenide flake, encapsulated between two hexagonal boron nitride layers. Hexagonal boron nitride is a large bandgap insulator, okay? And then we finished the device by adding a few layer graphene contact on top. And all this structure was deposited on top of a silicon and silicon dioxide substrate that was back contacted, and then just the top and back contacts were just contacted. And here I'd like to point out something that will be important for let's say the results later, and is that we decided to put here to make this hexagonal boron nitride layer 1 atom thick. So that means that our tunnel barrier is 1 atom thick, okay? And our idea with this device was to have the following. So by using graphene as a top contact, we wanted to have the chance to both load additional electrons or holes in the same device, okay? Which is not possible with conventional 3-5 quantum dots. So we fabricated the device and we cooled it down to 4 Kelvin. We measured photoluminescence, and this is a spatial map of the photoluminescence in the sample. So we have a background emission that coming from the to the exciton of this material. But then here you can see some bright spots. These bright spots correspond to the emission of single photon emitters in the material. So in particular, in this spot here, you can see a photoluminescence spectrum. We have 3 neutral excitons of 3 different dots that happen to be in our confocal spot, which is around 500 nanometers in diameter. So what happens when we change the voltage gate in the sample? So we get something like this. If we have a look at 0 voltage gate, we have these 3 neutral excitons, but now we can start changing the voltage gate, for example, decreasing it, and at some point, another electron can be loaded in dot A, another electron can be loaded in dot B, and we can also load an additional electron in dot C, and therefore achieving the negatively charged trion. And also for dot B, we were able to increase the voltage gate and have tunneling of an additional hole and having for the first time a positive trion in this quantum dots. So yeah, obviously we were very excited about these results because for the first time, we were able to control the charge state in our quantum dots in this tungsten selenide. But also on top of that, we observed a few things that were quite interesting. First one is that we observed a no-Stark effect. That means that the permanent dipole of this quantum dot is in plane, and therefore it was not sensing the electric field. And also, there are here some signatures, like for example, this continuous transition, that suggests that we have a strong tunnel coupling, strong tunnel coupling. So we wanted to investigate this in a bit more detail. So what we did was we investigated dot B because it has both the positive and negative trions, and we did, and you can see here the results. So we basically used a higher spectral resolution to investigate this. And the first thing we notice is that the neutral exciton is not a singlet emission line, but a doublet. And this is something very is typical of these quantum dots. Basically, this arises due to the fact that we have a fine structure splitting that originates from the fact that our quantum dots or confinement potential is not symmetric, okay? And this basically gives rise to two linearly polarized emission doublet that has is let's say cross polarized, as you can see here, okay? Interestingly, when for the, let's say, if we have a look to the negative and positive trions, we see that in this case we only have one emission line, so there's no fine structure splitting, and this can be understood by the fact that when you have a second electron or a second hole in the dot, basically you're removing the electron hole exchange interaction, and therefore there's no fine structure splitting, okay? But again, as I said, there was something else that going on here, and there were some signatures that were hinting or were giving us some clues that there was some ultra strong coupling between our, let's say, quantum dot and the Fermi sea of electrons. And these signatures are the fact that, for example, the plateaus don't overlap. Basically, you can see here that this plateau doesn't overlap with this, and this doesn't overlap with this one. We also observed the line with broadening of the transitions. For example, if we plot here the line width of the neutral exciton as a function of the applied voltage gate, you'll see that basically in all this region, the line width is constant, but as we start approaching the voltage gate at which we start having tunneling, basically, the line width increases. We also observed a strong bending of the energy transitions. This is basically a zoom of this region here. So again, when we are approaching the voltage gate at which we have tunneling, this energy, you can see the band is bending to lower energies. And what probably is more interesting is we also observe the presence of hybrid excitons, okay? And these hybrid excitons are this continuous transition from the neutral exciton to the negative trion, for example, in this case. And if to understand this, what one can do is to just write down a simple toy model, a Hamiltonian, where basically you model the initial state as a superposition of two states, okay? For example, the initial state is a superposition of a one state in which we have a neutral exciton in the dot and an additional electron in the Fermi sea, okay, and a state where this additional electron has tunneled inside the quantum dot, and therefore we have a negative trion, okay? This will be for the initial state. For the final state, again, we have a superposition of two states. After electron-hole recombination, we can have the electron either in the Fermi sea or either in the quantum dot, okay? So with this simple, let's say Hamiltonian, one can basically reproduce the energy dispersion that we observed. And for this, we only need to use two fitting parameters, which are basically the tunnel coupling for the electrons and holes in this side, okay? So this basically told us that actually what we have here is this strong tunneling and where the electron conserves the spin between the same tunneling between the Fermi sea and the quantum dot, and this transition conserves the spin, okay? And finally, since for the first time we were now able to have both positive and negative trions in our dots, so we were able to prove the G factors of these quantum dots for the first time, and we observed that well, both charged trions basically have very similar G factors to the neutral excitons, okay, which had already, the neutral excitons had already been, these values had already been reported before, but for the negative trions, this was the first report. So I hope I wasn't too fast with this part, but just to wrap up the results of this first part of the talk, I'd like to, well, I hope I convince you that it's possible to achieve Coulomb blockade in natural dimensional quantum dot, okay? And with a device like this, in particular, it's possible to have controlled tunneling of both electrons and holes in the same device. That, due to the fact that we used an atomically thin tunnel barrier, we had ultra strong and spin conserving tunnel coupling, which basically led to the observation of hybrid excitons. And that, thanks to this device, we're also capable of studying the magneto-optics of charged excitons for the first time. But now these results open, let's say, the doors to new experiments, I mean, for new research in two very different regimes. One regime will be a regime in which basically we try to cancel let's say, the coupling between our localized state and the environment, basically to have isolated spins to be able to manipulate them. And this can be done simply by increasing, changing the number of layers of this tunnel barrier. So basically we need to choose a thicker HBM layer. But we can also go to the opposite limit and say, and investigate new Kondo physics, right? Because if you think about what the Van der Waals platform offers you, we can replace this top contact by another material, for example, a ferromagnet with spin polarized, let's say, carriers. So yeah, I think there are nice things to do with this material platform. And now I'd like to, since I still have time, I'd like to show you how this research has evolved into a more recent research. And I'd like to point out a key difference between these two parts, and is that in this first one, the quantum dots were something intrinsic to one material, and then we use the heterostructure to control how these quantum dots interact with the environment, or let's say, to achieve gate tuning, okay, these quantum dots. But now in this second part, the quantum dots are something intrinsic to the heterostructure. So I need to have a heterostructure to create the quantum dots, okay? So what happens with transition metal dechalcogenides is that when you combine two of them, in general, you get a type 2 band alignment. So in the case of the heterostructures that I'll be using, which basically were formed by molybdenum selenide and tungsten selenide, we end up with a band alignment more or less like this, and which basically means that we have a fast charge transfer of electrons and holes, and this results in the formation of interlayer excitons. Okay, in these interlayer excitons, we have the electron and the hole located in two different layers. Okay, and obviously these interlayer excitons emit at lower energies than the typical intralayer excitons, so we can resolve them quite easily. On top of that, when you combine two different materials, as you have seen, what we have seen many times in this conference, well, one gets a more superlattice, right? Where with a periodicity that depends on the stacking angle and the lattice mismatch of these two layers. So it was theoretically predicted that this Moiré superlattice should give rise to a modulation of the optical bandgap, and this modulation could give rise to some let's say potential traps that could give let's say could lead to the formation of ordered arrays of quantum dots. Okay, in particular, the trapping sites are sites where the atomic registry shows the threefold symmetry of the, let's say, the monolayers that are forming the heterostructure. Top of that, theory also predicted that depending on the let's say on the trapping site and basically the atomic registry, we could have trapped excitons that should show different selection rules depending on if the, let's say, if the exciton has a spin singlet or a spin triplet configuration. Okay, so it turns out that this was demonstrated last year, well, experimentally demonstrated last year by the group of Xiaodong Zhu in the University of Washington, where they basically fabricated heterostructures with stacking angles of 60 degrees or close to 60 degrees and close to 0 degrees. And they observed narrow emission lines with circularly polarized emission and with very different G factors depending on the stacking angle. However, they didn't manage or they didn't demonstrate that these trapped excitons are single photon emitters. So we wanted to prove this experimentally. And for that, we fabricated a device that looked like this. Basically, we had our Moiré superlattice, was created by these two materials, encapsulated between two hexagonal boronitride layers again. And then we finished the device by adding a top graphene and a bottom graphene layer that we used to apply vertical electric fields, as we'll see later. So for this heterostructure, we chose to stack them, the two layers with 60 degrees stacking. This is what's known as 2H stacking. And this basically means that we have the key values of one material aligned with the minus key values of the other material, and vice versa. And if you think about the optical, the possible, let's say, optical transitions that we have for this configuration, basically we have two possibilities. The lowest, we have an interlayer exciton with a triplet spin configuration that involves the lowest conduction band. And then we have an interlayer exciton with a spin singlet configuration that involves this higher energy conduction band. So again, we fabricated the sample, we cool it down to 4 Kelvin, and we measured photoluminescence. And here I'm showing you the results of changing the excitation power. So for high excitation powers, we basically see two broad bands, which basically are these two exciton transitions. In fact, the energy separation between these two is basically the spin orbit coupling energy difference between these two bands. And once we start decreasing excitation power, what we see is that this band starts breaking into narrow emission lines. Okay, so this, well, here I'm showing basically this spectrum. So these narrow emission lines are these Moiré trapped excitons. Okay, and I want to show you that these trapped excitons show the typical saturation behavior with the excitation power of a two-level system, which basically confirms that these are trapped excitons. And also, well, we can spectrally filter them in this range and measure time resolved photoluminescence to get the lifetime. And also filtering this emission spectrally, we were also able to prove, and this was challenging, but we were also able to prove that the second order correlation of these emitters goes below 0.5, basically demonstrating that these are quantum emitters. And you'll see that the second order correlation function at 0 time delay is not going all the way down to 0, but I want to remind you or to show you that here we had some background that we couldn't get rid of it. So if you take the ratio between the areas, between this peak and basically the background, one can calculate what's the minimum G2 that we should achieve. And basically this is the dust line that I'm showing here. So this is exciting because it means that if we keep increasing sample quality, there's a chance that we can get nice single photon emitters with nice purity in this Moiré superlattices. But also, I'd like to show you something else. So if you think about it, these interlayer excitons are interlayer, which basically means that we have the electron hole in different layers, right? So that means that we have a large permanent out-of-plane dipole. So if in principle, by applying a vertical electric field, we should be able to use the Stark effect to tune the emission energy of these excitons. And here is what happens when you do that. So I'm showing here the spectrum for a few of these quantum dots, where basically we change the applied electric field. You see that I'm applying a bit more than 2 volts, and with just 2 volts, I'm able to tune the emission energy of these quantum dots in almost 40 milli-electron volts. Again, this is very exciting for us because, well, we've been working in our group for quite a long time now with 2-dimensional quantum dots, and these are the first quantum dots that we can tune their energy. I mean, let's say efficiently, right? And this means that for the first time, we are now in a good position to try to tune these quantum dots in resonance to cavities, for example, which we haven't been able to do because before we were relying on the fact that when you were exfoliating the material, you were lucky enough to get a quantum dot with the wavelength or the emission energy that you wanted, right? So this is no longer a problem with these quantum dots because just with, let's say, a few layers, like 5 layers of atoms, basically, well, a bit more because these are 3 atoms each, but yeah, just with a nanometric structure, you can have a 2-dimensional quantum dot with a controllable emission energy, and this is quite nice. And since I think I still have a bit of time, I'd like to show you that in these heterostructures,
Yeah, you have almost.
I have it, right?
Yeah, 5 more minutes. Sure.
Okay, thank you. So I'd like to show you also that in these heterostructures, the Moret-trapped excitons also show an interesting property, which is the spin layer locking. Okay, so if you think about it, in addition to having a heterostructure where we have monolayer and monolayer, we can fabricate a heterostructure. We have bilayer with a monolayer, right? So what happens with these bilayer materials is that they have an intrinsic 2H stacking. So that means that these 2 layers are rotated by 180 degrees, which is basically the same that 60 degrees thanks to the 3-fold symmetry, right? So when you think about how the band, let's say, the band edge states align, let's say in the key values, if you stack these 2 with 60 degrees, let's say you stack this one, the bottom one with this one at 60 degrees, you get K value aligned with minus K. But now, due to this intrinsic layer rotation, the top layer is again, let's say, aligned with the bottom one, right? So I want to show you and convince you that basically this gives rise to 2 species of interlayer excitons, okay, in this region, where basically we have the electron located either in the top layer or in the bottom layer. And this means that these 2 species of excitons, interlayer excitons, have different valley and spin layer pairings, right? Because for these excitons, we have a ground state, basically, that has parallel spins, and our key values are aligned. And for these AB excitons, here we have the K values aligned with the minus K value, and the ground exciton states have anti-parallel spins. So the way to prove this, well, you can measure the G factors of these interlayer excitons, and you can see here that they show very, very different G factors. This is not something particular of these 2 excitons, but yeah, it's reproducible for all the excitons that we found in the sample. Actually, we fabricated a second structure to prove that, yeah, this was actually what was happening. And as you can see here, this exciton showed an average G factor of -7, while this AB exciton show an average G factor of around -16, let's say. So these G factors can be very well understood just by the spin and the orbital involves in the bands, okay? So you can have a look in this recent paper where we have explained this in more detail. And combining these magnetic field results with the optical selection rules that we measured, we can basically conclude that our atomic sites, the atomic sites responsible for trapping the excitons, have this particular atomic registry. Okay, so again, I went a bit fast in this part, but you can have a look in this paper that we've recently published. And with this, I'd like to wrap up this second part and show you and tell you that I hope I convince you that we can trap interlayer excitons in the moire superlattice created by two rotated layers. That these excitons are indeed single photon emitters. That thanks to the large permanent dipole, we can use the Stark effect to tune the emission energy, and that we can create heterostructures where we have spin valley locking of these interlayer excitons. And with this, well, I guess again this opens some perspectives for future work. Where basically the one that I'm more interested right now is the Hubbard model of interacting particles in this moire superlattice. And before I conclude, I'd like to show you the results for a sample that I have right now in the Graphene, where basically like to tell you that in these devices we can also have an extra contact and change the doping in the layer, and basically this way we can control the number of holes or the particles that we load in our pockets in the moire lattice. And well, if you measure the G factor of the excitons as a function of the filling factor of holes, we see a huge change in the G factor, which basically is telling us that we're observing some phase transitions in this material, right? As recently reported in these papers for other heterostructures. And with this, I'd like to thank my collaborators in Heriot University and also in the University of Valencia and our Japanese friends for providing hexagonal boronitride material. And well, thank you for the introduction, for your attention, sorry.
Well, thank you very much, Mauro, for such an interesting talk. So I think we have still time for one question. So you can use the chat or just ask to Elena or I to open the microphone.
Yeah, well, you can unmute yourself if you have any question. Anybody?
Sorry, I stopped sharing. I think I stopped sharing.
You can share it again.
Okay. Yeah, I think I can.
So I have a question, Mauro.
Yeah.
I don't know if I missed it, but did you mention the temperature at which you made the measurements?
I did, but very fast.
Okay.
4 Kelvin. Yeah, these are all measurements are done at 4 Kelvin. Yeah. And what happens is that we have very shallow confinement potentials. So if you don't, well, if you increase a bit the temperature, yeah, you have thermal excitation, and basically you no longer have trapped excitons.
Sure.
I think they survive until 25 Kelvin, something like that.
Okay. And for the preparation of the samples, for the stacking, I guess it is very tricky to do that. I think all of we know, right?
Yes, it's very tricky.
And I guess you do this in a control environment with nitrogen or
exactly
or something to avoid this water or these kind of things, right?
So yeah, actually here what we have a glove box that we put together a couple of years ago, and we work in an argon environment, and we do everything inside. So we do the exfoliation, transfer, and in situ characterization inside, like for example ellipsometry or AFM.
Okay, so everything is in the glove box, right?
Yeah, and once it is encapsulated with hexagonal boronitride, we can take the samples outside and go to the cryostat. Yeah.
Okay, we have a question
from Pablo.
Yeah.
Pablo, I believe you have the microphone open, so you should.
Can you hear me?
Yeah, I can.
Yes.
Okay, yeah, thanks for the talk. I have a question which is related for both parts. So, well, from the first part, both monolayer HBN and monolayer tungsten selenide have broken inversion symmetry, so they can present piezoelectric properties. So, if you have bubbles or wrinkles in your devices, this can produce these charges or things. And in the second part, also in the system of molybdenum selenide and tungsten selenide, also wrinkles and things like that can produce changes in the optical properties. So in the end, the question is, in your devices, do you have bubbles, wrinkles that can change the strain, that can also change the properties?
Yes, and the answer is yes. This is a problem that I guess everyone else working in this field is experiencing. So when you transfer two layers. You can, you always get, even if you're very good at it, you always get some air trap or some bubbles or wrinkles. And actually, in the first case, in the first part of the talk, I didn't mention it, but here, this quantum, can you see the slide? Yeah. In this this quantum dot here, what you can see here is basically a wrinkle in the sample.
Yeah.
That basically, in this case, we use to get the quantum dots.
So then, how do you account for the possible piezoelectric effects in that case, or these electronic effects?
To be honest, I might be wrong, but I don't think that, well, I might be wrong, but I don't think the piezoelectric effect would change the, let's say, the optical properties.
Well, I don't know. Just
I don't. Well, to be honest, I don't think we ever considered that.
Okay. Yeah, because it's been observed that for example, in monolayer HBM bubbles, there is a kind of extra electric field around the bubbles due to this strain. So I don't know if this can affect the optical properties because of these extra charges.
I don't know what to tell you, because every device that we prepare is going to suffer from the same. So what I can tell you is that these quantum dots are the typical properties that we've been seeing in hundreds of quantum dots. But I don't know if these are affected by this piezoelectric effect by some extent. I don't know.
Okay, thanks.
Okay, thanks. So I think it's time to close this session. So thank you very much, Mauro, for this talk. And now it's time for Elena to close this hour session of this meeting. Elena, are you there?